Well, let's say create a path to the front here. There we go. I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for this opportunity we have to meet and study your creation. And just again, I pray that you'd give us insight and just help us to glorify you, what we do learn. In your name I pray, Lord Jesus. Amen. Let me continue with my story of the Dirac Delta function. So we introduced it as this kind of very strange thing that turns integration into evaluation. As I told you, it's kind of a mathematical device for capturing something that just happens at an instant. It has other uses, like, let me, I can remember. So the Dirac Delta, before I get back to the differential equations proper, let me just give you another application of it. If we have rho of R is equal to the charge density, so like dq dv, the charge per volume, and you want the formula for the, suppose you've got your charge here, q, right, at position vector, say r1, then what you do is you just do q times the three-dimensional Dirac delta of r minus r1, right? And what that is like mathematically what happens is if we integrate like the charge density over the volume, right? Let me say this is some volume v, all right? Well, it's either equal to q if r1 is an element of the volume, or it's 0 if the point is not in the volume. And that is exactly the concept of a point charge, right? That's what a point charge is it's a finite amount of charge at a mathematical point. Now, there's a lot of interesting mathematics here as well. Like you guys maybe you know, maybe you don't know, but Gauss's law is that the divergence of the electric field is the charge density divided by epsilon naught, right? And maybe you also knew that the okay, so for the rest of this, let's, for the sake of making things nice, let's let r1 equal to 0 and what follows, just to declutter things. All right. So I'm gonna put the charge at the origin. If that's the case, then we know the formula for the electric field, the Coulomb field, right? It's q over 4 pi epsilon naught. Well, r hat over r squared using physics notation. Here, r is the spherical radius. We usually use rho in physics, in Calc 3, but obviously I don't want to use rho here because rho is the charge density in physics. So, oh well, there's only so many letters to go around. But you notice that if we calculate the divergence of the electric field, well, how does that work? Right? Well, look at this. The flux of the electric field over the boundary of some volume, right? That's equal to what? It's equal to the triple integral, right, over the divergence of the electric field over the volume, right? This was the divergence theorem. Remember that from Calc 3? The divergence theorem at the end? Okay, so apparently that's supposed to be equal to, what is it? Apparently it's supposed to be equal to, well, 1 over epsilon naught, the integral of the charge density dV. Right? Because I'm telling you, Gauss's law says the divergence of the electric field is the charge density divided by epsilon naught. But how does that work? I mean, that integral is what? It's equal to what? It's equal to q over epsilon naught if 0 is an element of the volume, or in 0 if 0 is not an element of the volume, right? Okay. Now, if we take the volume to just be like the ball of radius r, then the integral over the boundary of the ball of radius r of E dot dA well, that's explicitly the integral of, q over 4 pi epsilon naught r hat over r squared dot with r squared sine phi d theta d phi. Ah, come on. Use your imagination. There's a phi there. Now here, this is physics, so the theta goes from 0 to pi, and the phi goes from 0 to 2 pi. So, lo and behold, that gives us q over epsilon naught. So everything would seem to be consistent, right? But have you ever actually tried to calculate? Have you ever actually tried to calculate the divergence of this right here? If you actually calculate the divergence of this, it works out to 0. So it seems. Actually, it works out to 0 as long as you're not at the origin. That's the truth. It works out to 0 as long as you're not at the origin. And in fact, to repair and include the enjoyment, so this is only for r not equal to 0. If you study it, and I've almost got all the pieces on the board right now, but if you study it, the divergence of r hat divided by r squared, well, what it is 4 pi, the three-dimensional Dirac Delta of r. And so this formula I just wrote in purple, it repairs the divergence theorem to make it extend to the case that you've got this, point-like divergence in your field in the middle. Like, technically speaking, the divergence theorem doesn't hold for the Coulomb field on the ball. The reason being, there's a divergence in the field at the origin, so you really don't have any right to apply the divergence theorem there. Which is why we would get a seeming contradiction if instead of doing what I did here, we had jumped ship and went like, oh, well, that's 0 everywhere except for where it's not defined, and just, naively had said the flux is 0, but the flux isn't 0. Through direct computation, it's q over epsilon naught, right? That would be a contradiction. And the contradiction is brought to you courtesy of ignoring the fact that, yeah, the divergence is 0 everywhere except where it's infinite. And an infinite divergence at the origin actually leads to a non-trivial integral. And that's all wrapped up in this one little identity right here. The divergence of the inverse square field is 4 pi times the three-dimensional Dirac delta. And so there's also like two-dimensional Dirac deltas, all right? And you can view all of these as a sort of a means to repair the divergence theorem to point-like singularities that are manageable. At least this is the viewpoint of Griffith's electrodynamics, which I'm teaching at the moment, so there you go. Let me shut up about that. This comment only appears in your semester. In no other semester am I teaching this other class, so anyway, can I erase? I'm going to erase. Actually, I'll work over there. So let us work a problem. Here we go. Example 1. Let's try to solve y prime prime plus 4y prime plus 4y equals to, 3 Dirac delta of t minus 7, given y of 0 is equal to 2, and y prime of 0 is equal to, I don't know, 13 there. So last time we worked out that the Laplace transform of the Dirac Delta of, say, t minus a, right? We worked that out. It was simply e to the minus as. Remember, that's what we did that last class. You guys remember? Okay. Okay, so let's take the Laplace transform of the differential equation. What do we get? All right. So we get s squared, big Y, minus s times what? I guess I should remind you guys, the Laplace transform of y prime prime is equal to s squared times big Y minus s times y of 0 minus y prime of 0, right? So I do s times y of 0 was 2, so I do s squared minus 2s minus 13 apparently, plus 4 times, big parentheses are your friend, s times big Y minus y of 0, which was 2, right? And then 4 times big Y. That's all equal to 3 e to the minus 7s, right? So this is the technique. We take the differential equation, which is given initial conditions, right? Take the Laplace transform of it, and then our next move is to solve for big Y, right? So, all right, so we got s squared plus 4s plus 4 times big Y is equal to, looks like 2s. I got a plus 13 and then a plus 8, also known as plus 21. And then, of course, plus 3 e to the minus 7s. All right. So far, so good? Yeah. All right. So now we can solve for big Y. Big Y is 2s plus 21 divided by, what's s squared plus 4s plus 4? Can you recognize what that is? S plus 2 squared, right? All right, so that's what we're up against. And then we've got plus thrice over s plus 2, quantity squared, e to the minus 7s. All right. That's almost nice. Let me just make one little adjustment before we go to the inverse transform. So what I'm going to do is I'm going to do 2 times s plus 2, all right? And then I've got plus, well, that's, plus what? No, I'm not done yet, right? Like, you guys help me out. What am I, Oh man, I never moved the camera. Well, at least everybody's here, so it doesn't matter, right? I should give another surprise attack mission, but it seems to have no effect. Like, I gave a surprise attack mission last Friday out of spite for a bunch of people who've been missing, and now a bunch of people are missing again. Like, you guys think I'm not going to do it again? I don't know. I might. Those of you who are here are like, well, I'm here, so do it.
Plus 17.
I heard a plus 17. Do you guys agree? How do we check? Yeah, multiply it back out, see if you get back where we started, right? It's not magic, it's just algebra. So, well, that's good, because if we do that, then we have found our way to the very nice formula. Y of s is 2 over s plus 2 squared, right? Plus 17 over s plus 2. Oh, there's not the square in the first one. But there's a square on the second one, right? Because the s plus 2 would be canceling. 3 over s plus 2 squared e to the minus 7s. Now this is very nice what I just wrote, because that we can straight up take the inverse transform of using our various, rules. All right, so the inverse, I guess let me go off on the sidebar here, right? What's the inverse transform of 3 over s plus 2 squared times e to the minus 7s? What's that going to be equal to? That's supposed to be equal to the inverse transform of 3 over s plus 2 squared, right? At time t minus 7 times the unit step function of t minus 7. Now, the way it's written on your sheet, if you look, is that theorem. It's like the next row up from the bottom. We take the inverse transform of e to the minus as times f of s. It's little f of t minus a. Well, what is little f of t minus a? That's the inverse transform of big F, right? So I take the inverse transform. This is like my f of s, all right? This right here is just another notation for f of t minus 7, okay? So what is, in my current notation, what is f of t? We got what? We got 3t e to the minus 2t, I believe. Right? So here we go. Y of t is the inverse Laplace transform of big Y of s at time t, which is in fact equal to twice e to the minus 2t plus 17 t e to the minus 2t plus 3. Now I got to replace t with t minus 7. So 3 times t minus 7 e to the minus twice. Again, replace t with t minus 7. And then finish this off with a unit step function like that. And there you go. That is the solution. And again, we see this like, there's two pieces, right? There's the piece without the unit step function, which is essentially just the response of the system to the initial conditions, right? And then when that delta function gives it a tap, like with a hammer, kind of, at time 7, then the solution changes forever thereafter, and it induces this extra, response of the system to the delta, the unit of the, I guess, 3 impulse in this case. Yeah. Any questions? You guys understand? Is there a particular thing here I can elaborate what I did? Okay. All right. Well, with that, I'm going to actually now do something rather boring. I'm going to go back to Laplace transforms and do some more of those. All right. By the way, the Dirac Delta problems have the privileged position in this class of, the only way, as far as I know, the only way you can do it is with Laplace transforms, right? So like, if I want to force you guys to use Laplace transforms without saying it, an easy way to do it is just say solve this and just put a Dirac Delta function in there, right? Because the only technique we have to handle the Dirac Delta function is the Laplace transform. Now there are other techniques. There are other quote-unquote integral transforms. For example, the Fourier transform, which can handle these things. But the Fourier transform is not something that I typically cover in this course because it's a little bit, Well, the problem with the Fourier transform is we really do need a little bit more competency with complex analysis. And, well, that's a whole other course we have to take here, you know. So ideally, we'd have a course which had this and the complex analysis course as prerequisites, and then we could do a proper Fourier analysis course, which is of interest to engineering, right? For sure. Dr. Schmidt is also very interested in that topic. So if you're ever interested in a reading course in that or something, talk to Dr. Schmidt. He might be able to talk him into it. You never know. But again, reading courses are not on your DCP, so no one cares. All right, let's see here. It's kind of funny the way things are set up. But where was I? Oh, yes. Oh, man. Oh, there it is. It's I've lost my complicated examples. So let's talk about. Let me entitle this "Less Obvious Laplace Transforms." So just to kind of give you a sense of where we are and where we're going, I've already shown you the main story. All right, we have done the central thrust of the material. We take the Laplace transform, we take the inverse Laplace transform, we solve the differential equation. And so I've shown you some pretty standard examples at this point. So now I'm kind of going back and I'm dealing with some more nefarious calculational issues, and we'll see what we're up against. So example 2. Suppose you were going to calculate the Laplace transform of t times the sine squared of t. How would you do that? So remember the theorem we had? Multiplication by t is what? It's the derivative with respect to s, right? So we have to take the derivative with respect to s of the Laplace transform of sine squared of t. That was one of our early rules, yeah? So then how do I take the Laplace transform of sine squared? I guess what we should do, can you guys tell me how to convert that to elementary trig functions? What is it? 1/2 what? 1 minus what? Cosine 2t, yes, cosine 2t. All right, so there is doubt. Very good. I will show you a way to remove the doubt in a moment, but let's see here, DDS of, so that's Laplace transform of 1/2 is just, well, I'll leave the half out front, right? Let's pull that half out front because we don't want to keep dealing with that. So I'll pull the minus 1/2. I got a minus 1/2 out front, right? All right. Then I've got Laplace transform of 1 was 1 over s. Remember that? The Laplace transform of cosine 2t is in fact s divided by s squared plus 4. You guys do have a sheet with all these things on it, right?
Yep.
But do you know why I can calculate faster?
Because you've done it for years.
Because I've done it for years. That's true. I've done nothing but math my entire adult life. That's part of it. True. But the other part is because I've got all of these things memorized. I never look at the sheet. I just know the transforms of cosine and sine. Now for me, the way I've learned those is to derive them year after year after year. I don't suggest that you teach differential equations a bunch of times to get better at it. It seems like an impractical way to get a better grade in the course. I don't know how you do that in preparation, really. Seems like a challenge. Well, time travel maybe, but I don't know. Maybe maybe you'll be able to load stuff into your with the neural link before long. Let's see here. Sorry. Oh my goodness, we're differentiating a quotient. What are we going to do? I would suggest the quotient rule. So the derivative of s is 1. So I've got s squared plus 4 minus s times derivative of the denominator is 2s, all divided by s squared plus 4 quantity squared. Yowzers. clean it up, and we're done. So I'll leave the half out front. I'm going to distribute that minus through. So you got like a 1 over s squared here. And then plus, how does that work out? We got, that's a minus, I guess it's a 4 minus s squared, right? So 4 minus s squared divided by s squared plus 4 quantity squared. Now we have not, I don't think at this point yet, seen, I might have done one isolated example, but for the most part we haven't encountered stuff that's quadratic in the denominator. Why do we have something quadratic in the denominator for s? Where's that coming from? It's like a t times the sine, right? How do you get t times sine? From a repeated complex root in the constant coefficient problem, right? And the solution set to those come with like t times sine, t times cosine. So this is not surprising that we have a quartic denominator in s, because if you think about the corresponding characteristic equation here, it would be fourth order with a repeated complex root. All right, great. Now there was definitely a problem here, right? Because like this right here will stop you dead if you don't know that, right? Let's do another. All right, come on. How about we calculate the Laplace transform of, I don't know, sine t cosine 2t. How would you deal with this? You can look at the sheet all day long. It will not help you, right? It will not help. You need trigonometry here is basically what it is, all right? Let me show you how have I showed you this guy? I don't know if I've showed this guy to you or not, I can't remember. But for me, my way to do trigonometry is this. I go, okay, so e to the I theta is cosine theta plus I sine theta. And e to the minus I theta is cosine theta minus I sine theta. Because sine is even, sine is odd, cosine's even. If I take these formulas and I either add or subtract them, I can derive from that cosine of theta is 1/2 e to the I theta plus e to the minus I theta. And I can also derive that sine of theta is 1 over 2i e to the I theta minus e to the minus I theta. Notice the similarity of these formulas with the defining formulas for hyperbolic sine and cosine, right? The analogy between sine and cosine and cosh and sinh is deeper than you may realize. If you want to fully understand that analogy, come take the complex analysis course or variables course. All right, so look, so before I can do that, I'm going to face the music here, which is that sine of t times cosine of 2t. So, all right, that's actually 1 over 2i times e to the it minus e to the minus it times 1/2 e to the 2it plus e to the minus 2it. So I'm literally just substituting in the arguments for theta in those patterns. And then what comes next is just algebra. Just do algebra like usual. It's true, theorem, if you have e to the I theta times e to the I beta, guess what? It's e to the I theta plus beta. So it works just like you want. And so when I multiply this out, I've got, like 1 over 4i out front, and I get an e to the 3it, and I'll do the last one next, minus e to the minus 3it, then I'll do the this one times that one. That gives me plus e to the minus it I wanted to do this one first. So I got e to the minus, it doesn't really matter, I can just rearrange them next, but I get minus e to the it, and then plus e to the minus it. All right? And then, all right, so that's actually 1/2 of 1 over 2i, e to the 3it minus e to the minus 3it, and then minus 1 over 2i, e to the it minus e to the minus it. Now you might be wondering, why am I doing what I'm doing? I'm doing it so it's back in the pattern of the formulas I have there. All right? So now I can go, oh, okay, this is like theta equals to, so this is actually 1/2 what? Recognize what we're looking at, making a substitution. That's sine of what? Match the pattern, what you got? Sine of 3t, right. So we get sine of 3t, and this one is simply sine of t. But there's a minus, so minus sine of t. Now, I can take the Laplace transform of sine t cosine of 2t with ease, because it's actually just 1/2 the Laplace transform of sine of 3t, yeah, minus sine t, also known as 1/2 3 over s squared plus 9 minus 1 over s squared plus 1. There you go. That is the Laplace transform that we're looking for. The thing that was in the way for us was trigonometry. Yeah.
Is it more straightforward to do this with convolution?
No. I don't think it's ever more straightforward to do something with convolution that can be done with algebra, because convolution is integration, which is herdy. But if you're really good at integration, maybe I'm wrong, you know. We should talk about convolution, though. That's a good question. I'm almost done with my tricky transforms here. Let's see what else I got for you guys. But my larger point here, folks, is just that this method I just used to derive the trig identity, it has wide application. Like, if you had forgotten, like this one, sine squared. If you forget sine squared is that, you can easily derive that with this method as well, right? You just do, 1 over 2i, e to the it minus e to the minus it, square that thing, right? That gives us minus 1/4, e to the 2it minus 2 plus e to the minus 2it, which is actually 1/2 plus 1/2 of 1/2 of e to the 2it plus e to the minus 2it, which, by the way, is 1/2 of 1 plus cosine 2t. There you go, that's the identity. If you learn this method, every trig identity that you could possibly forget, you can derive. Now, it's always faster just to remember the trig identity, obviously, right? But anyway, this is the technique of imaginary exponentials for trigonometry. All right. So now that I got that out of my system, let's go back and talk more about inverse transforms, right? Let's see here. Oh, let me use the projector. You asked about convolution. Let's talk about convolution, yeah. Yeah, I should have a surprise attack mission posted later today. I haven't gotten to it yet. I'm sorry, guys. All right, let's see if I can See, I can wrangle up here. All right. There's actually a couple things while I got the notes out that I should talk about. So we've always been working problems where, I'll come back to the convolution in a second. Yes?
I was just asking, I mean, you're about to run out of surprise attack missions. Are we just going to go straight on to boss fights, or are you planning to add?
I'll just add them because I'll just drop more.
Okay.
You would like for there to be more, because then I drop more that were bad, right? So more is better. So that's the light also that you should look at missing Friday, like last Friday. It's like, you know, yes, it would have been nice to come and get the easy free 20 points, but on the flip side of things, that means I'm closer to maybe bumping, I don't know, I guess it's still a net loss, but whatever. Oh, come on. What? Dudes. Hello? Connected inputs are yes, HDMI, that's what I'd like to input. Come on. You can do it. Ah, yes. Before I get to convolution, let's just take a second to look at this example. And maybe I'll try to put this in the surprise attack mission as well, just so because you won't understand it until you work one out for yourself, right? But what do you do if you don't have data at time 0, right? In the real world, not everything comes nice and pretty and packaged cleanly with time 0 data, right? Maybe you got time 10 data or something, right? So how do you deal with that? Well, this problem's about that. Suppose you're given, you know, data at time pi, which is just going to make things prettier. Time pi, you know, the real world time pi example, yeah, great. But all right, setting aside my hypocrisy. We got here is, so what you do is you make a substitution basically. I let y of t be w of t plus pi. In so doing, my new variable y has initial data. It has data at time 0, I mean. Technically speaking, the word initial data does not force time 0. An initial data problem is just meaning that all of the data you have for your differential equation is given at the same independent time variable. So you don't have information from like time 1 and time 3. You have all information at time 1, or you have all information at time 3. This is what makes it an initial value problem. Initial value problems are nice. We can solve those. They have unique solutions. The theory is beautiful. If you give data for differential equations at different times, like time 1 and time 3, there may or may not be a solution that satisfies both of those data points. Those are what's known as a boundary value problem. Those are much more subtle. We'll talk about those next. Excuse me, after we talk about series solutions. But that's the last thing I talk about in this course, is the boundary value problems. Anyway, so great. So y of 0 is w pi. Y prime of 0 is w prime of pi. So all of a sudden, we're back to the usual thing. And also, the cool thing is with this substitution, is the differential equation is the same stupid differential equation, right? It's still just, like, if you just evaluate the, we got to be careful because you have to replace t with t plus pi to get to the y equation from the w equation, right? And that does have an effect over here, right? Instead of having 8 to the pi minus t, when I plug in t plus pi, I get back to minus 8 e to the minus t. And so then I have this differential equation y, which I can do the usual thing, Laplace transform, solve for big Y, make it nice, inverse transform, there's your answer. But that's not the answer, that's not the final answer, that's the answer for the transformed variable. Then I have to do the inverse thing. W of t is y of t minus pi, you see. And when I do that, lo and behold, I have solved the initial value problem where the initial data was at time pi rather than time 0. This is the simple, so like we don't talk about this a lot because it's a simple trick that you can apply to every problem. We just focus on data at time 0 just to keep things nice and neat in our examples. But this is something you should know about because you might need to apply Laplace transforms at some time other than 0, and this is how you do it. Okay? So I'll make up an example in the surprise deck mission where you'll get to do this, okay? So just remember, as you're working on that problem, you can look at page 197, example 6.3.17, to help you see what to do, okay? And I'll try to put some sort of like training wheels on it in terms of like make a W blah 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 substitution, junk like that. But all right, hopefully the training wheels won't be destructive. Sometimes I give hints which are not helps. I'll try not to do that. All right, so all right, let us go over to. I'll come back to some of this stuff we're skipping, but since you guys asked me about convolution, let's talk about that at the moment. Convolution is defined as such, all right? So the convolution of two functions, f star g, is defined to be the integral from 0 to t of f of t minus v times g of v dv, all right? So for example, if you calculate the convolution of t and t squared, you're doing this integral, and lo and behold, it turns out it's 1/12 t to the fourth. Whatever that means. All right, great. So the properties of convolution are, it has some nice properties. It's commutative. It's distributive across addition. It's associative, which is super nice, right? And the convolution is 0, 0. So what does convolution have to do with the Laplace transform? Well, let's see what that is. So this is the convolution theorem. Oh no, I think I never moved the camera. Maybe I did. I don't know, I can't remember anything. Ay, ay, ay. No, I didn't. All right, sorry people at home. Go back and look at page, what did I say? 197. So here's the way. This is amazing. This is the convolution. The Laplace transform of the convolution is the product of the Laplace transforms of the functions convoluted. Perhaps more interestingly, the inverse Laplace transform of a product of S is the convolution of the inverse transforms. This is a gateway to calculating inverse Laplace transforms that we couldn't do up to this point. All right, like this opens up a whole new vista. And the calculation down here is not especially important. I always get confused about something in there, so let's just kind of gloss over it. I mean, I understand it completely. There's nothing to talk about there. It really is, I mean, I'm just joking. It is a somewhat natural calculation. And if you look at this, basically, another way to look at this is if you were to assume that this equation held, you could derive the convolution formula from this assumption. Like that's another probably thing you could do there. Anyway, let's see how it works. Ah, the double scrolling, it got me. Ah, I hate you double scrolling. The worst. It got us all the way over to the Frobenius method. Whew, that's a bad place to be. All right, so suppose you're trying to solve y prime prime plus y equals to g. All right, we take the Laplace transform. We get s squared big Y plus y equals to the Laplace transform of little g, which we'll call big G. All right, this brings us to 1 over s squared plus 1 times g of s. We have a product of functions of s. Well, this is made to order for convolution. When we take the inverse Laplace transform of this, we have the inverse Laplace transform of this f of s times g of s, right? Which by the convolution theorem is the convolution of the inverse transform of this with that. But the inverse transform of 1 over s squared plus 1 is exactly sine of t. So the answer is sine of t convoluted with g of t. Which is, what does that mean? That's an invitation for writing down an integral, right? Which I hopefully do next. Well, this one I actually do. All right, so I'm taking g equals to cosine, and so basically my last problem, you could put g of v here. So like the last problem basically said The solution is integral from 0 to t, sine of t minus v times g of v dv, all right? That's the general integral formula that the convolution theorem would derive for us. And then here, if I have the particular function cosine t, I've got this, which then gives me that, which then I can integrate, and I get, I get 1/2 t sine t. That's actually kind of cool, because we've just derived multiplication by t in the repeated root case for the imaginary case. That's kind of neat. We've derived multiplication by t from convolution. Yeah? Just like that. You could do a similar problem, similar example with, well, that's probably what this is. Let's see. So y prime prime minus y equal to g of t. And this time I gave us initial conditions, 1 and 1. So I take the Laplace transform, yeah, and then I solve for big Y. So I've got this piece here, which easy peasy, that inverse transforms to e to the t, right? And then we're going to use the convolution on this product over here. So we get the, I guess I'm partial fractioning this, right? But this isn't surprising. I told you guys about this before, right? This is cosh. Excuse me, that's sinh. The inverse Laplace transform of that is sinh. But anyway, there's the inverse transform. So the solution then, inverse transform of y, is the first piece gives me e to the t, and this gives me the convolution of sinh with g, which is explicitly e to the t plus that integral. Now, where are these integrals? Is there another way you could understand where these integrals come from? Do you guys have any ideas? How else could you produce an integral solution for these problems? How did we find an integral solution before? For like an arbitrary forcing function. What technique did we use? You guys remember? Simpler days, before we had all these Laplace transforms and eigenvectors. Back in the constant coefficient part of the course, after we did the annihilator method, undetermined coefficients, the final boss of the non-homogeneous problem was variation of parameters, right? You could also derive these integral formulas with variation of parameters, in fact. It's true. Somehow variation of parameters works out to this formula. Now, and here's one just to show you, if you want to take the inverse Laplace transform of 1 over, a quartic, just 1 over s squared plus 1 squared, convolution can do it for you. It's just a pain, right? Because this is the inverse transform of f and g, where f and g are both equal to, 1 over s squared plus 1. So I end up convoluting sine with sine. And the convolution of sine with sine, it works out to that. So going back to your question, should I use convolution? Convolution is like a weapon of last resort for me. It's much like variation of parameters. I want to know about it. I want to understand it. It's very, very important for the theoretical aspect of this study, especially as it regards to engineering, because convolution is what you guys need to pair together with your concept of the transfer function to understand how the system propagates signals through. All right, it's the transfer functions like the reciprocal of the it's the inverse transfer. Well, it's basically 1 over the characteristic equation in S is the transfer function, and you want to take the convolution of that with your inhomogeneous term to find the non-homo solution. The double scrolling got me again. Anyway, I will try to write you guys the next exciting surprise attack mission, and then you guys can bring it back to me Monday, I suppose. Thanks, everybody.